All right, so we just looked at this example of a population model. I think this was for Birmingham, Alabama, in the last lecture. And so now we have this model and we're going to use it for some stuff. So let's look at the questions. According to the model, in what year will the population of Birmingham fall because we are decreasing to 200,000? So again, this is an elapsed time model, as all of our exponential models are. So we're going to, I went ahead and entered this function in the calculator, and we want to know when we get down to 200. So I'm going to go to the table. I'm just going to start at 0, and this gives me an idea of my x max. So the intersection is going to occur sometime around 21 to 22. So if we go, actually this would be fine, 0 to 40, that would be plenty. And then we can do zoom fit. I just graphed the function, and now I'm going to find the intersection as usual. And it looks to be 21.957. Now, the question actually asks for the year. And so if we start in July 1st of 2000, 21.96 years thereafter would put us in 2022. Okay. Other questions. Use the model to predict Birmingham's 2010 population. Well, that one's pretty straightforward. That's just going to be evaluating. And I forgot, oh, we started in 2000, right? Okay. So we're just going to evaluate the model. For 10, that's 222.2.30. The 2010 population was actually 212, so we want to find the model error. The model error is just actual minus predicted, so that's 212.24, oops, minus the answer we just got, and that's our model error, -10. Now if we want to get the percent error, we divide the model error by the actual value, which is 212.24, and multiply that by 100, and that's our percent error, -4.73%. Finally, by how much does Birmingham's population decrease each decade? So this is asking for your 10-year decay rate. And we have the annual decay rate, 0.0088, and the associated factor. The factor is actually what we need right here. So that's our annual factor. We need to raise that to the 10th power because we're going from annual to decade. That'll give us our decade factor, and then we can transform that into a rate. So that's 0.9912 raised to the 10th power, and 1 minus that value times 100 to get the percent form is 8.45 or 8.46%. Okay. All right. So that's some more examples using exponential decay models. in a sense, that's sort of it. There's a lot more examples that we're going to do, but there's really no more completely new ideas or anything. But looking at examples is good, so we will do a lot more examples. In any case, just to review what we've gone through in this section, we have our basic exponential growth model. Now, I'm writing growth rate right here because that's the form that this is in, but keep in mind that this growth rate could actually mean decay if it's a negative number, all right? So I'll put growth in quotation marks because if the growth rate just means the form. If it's actually growing, then r will be greater than 0. But if it's actually decaying, then r will be a negative value. Okay. And hence the factor will be larger than 1 or smaller than 1 accordingly. Then we have these relationships between the factor and the rate, very important. The growth rate. And then finally we have the conversion between the decay rate and the growth rate. And that's pretty much the essence of it all. But then, when you get into the details of solving problems, sometimes things can get a little confusing. So let's look at some more examples. Suppose we have a quantity that decreases by 11.25% hourly. How much does it decrease each day and each minute? So this whole question is all about changing our time unit, and we don't even know how much of this stuff that we have. It doesn't matter. The important thing is this rate. So our R value would be negative 0.1125. That's our growth rate. The growth rate is negative 0.1125. I need this because I need the factor. So the factor is important because that's what we actually use to transform into different units. So this is my hourly factor. If I want to go into days, I need to raise this to the 24th power because there are 24 hours in a day. Let me actually write that. And then we're going to compute this value. And remember, we're going to get a decay rate here. So if we get a negative growth rate, we need to make it positive. So don't forget that. But 1 minus 0.1125 to the 24th power. That's our daily factor. And then you can either subtract this from 1 and change and not change the sign, or subtract 1 from this and change the sign. It just depends on how you want to go about it. But if I just do minus 1, that right there is my daily decay. That's my daily growth rate. So if I write it like this, I forgot what my value was. 0.94, let's call it 0.943. So my actual decay rate is 94.3% daily. Let's look at the minute decay rate. So again, I'm going to go back to the factor, but now I'm going to raise it, instead of the 24th, I'm going from hourly to minute, so I'm going to raise it to the 1/60th power. And then beyond that, it's exactly the same set of steps. So you would subtract 1 from this, then you'll get a negative number here because it's negative growth, and then I'll change the sign. Now, in the previous example, I think I did it the other way, where I was actually subtracting. I did 1 minus all this, and then I didn't have to change the sign. I don't mean to be confusing by that, but it doesn't matter which way you do it as long as you are aware that you are either finding the growth or the decay rate. And know what you should end up with. So if you know you should end up with a decay rate, then act accordingly. Okay, so in this case, that means if I get a negative growth rate here, I'm going to change the sign. So I'll just skip to my solution. Here it is, raised to the 1/60th power. And then as you see here, -1, that gives you a negative number. And then we multiply by 100 and change the sign. And so there it is, 0.2%. Okay.